This is Mrs. O'Neill for AP Chemistry, Chapter 13, Section 1, Properties of Solutions. Look over those key terms on page 546. In Chapters 10 and 11, we explored the properties of gases and liquids. Most of the discussion focused on pure substances. However, the matter that we encounter in our daily lives, such as air, seawater, and sand, is usually composed of mixtures. In this chapter, we examine homogeneous mixtures. So here on the bottom, we have two examples, salt water and hydrochloric acid. A sinkhole forms when the roof of a cave weakens from being dissolved by groundwater and suddenly collapses. One recorded sinkhole swallowed a house, several other buildings, 5 cars, and a swimming pool. You will learn how the solution process occurs and the factors that influence the process. So section 1 is the solution process. You should have watched the intro lesson. Here are some of my notes. We usually think of solutions as liquids, but remember, solutions can be gases, a mixture of gases like air, and a mixture of solids or an alloy like steel. Gave you a nice flow chart as always. And we want to remember that solutions must be homogeneous, at least at this point to the naked eye, does not scatter light, and cannot be filtered. So he talked about separation by chromatography and distillation. And again, all of these things are based on those IMFs, and that's why we had to learn those first. So he explained in more detail about chromatography. There were 2 kinds, the paper chromatography and the column chromatography, and the distillation process based off of vapor pressure. He gave you that simulation from PhET, and he kind of went through adding salt to water, how it increases the conductivity, and then he did a few other things to that. Talked about the formation of a solution takes and releases energy, and we're going to talk about the different solution process. Part of those processes are going to be endothermic, and part of those processes are going to be exothermic. So the overall process, of course, is going to be based off of 3 things, 3 steps, and of course the overall process then can be endo or exo depending on those 3 steps. And then towards the end, or in the middle section of this chapter, we're going to be dealing with molarity, with the calculations of molarity. Onto your packet of notes. As always, I suggest pause, fill in the notes, and then play to hear my words. So the objectives for this section is to figure out what happens at the molecular level when substances dissolve. And again, we're going to pay attention to those IMFs. We're going to recite the 2 important aspects of the solution process as the natural tendency of particles to mix and the changes in the energy. So what is a solution? Consists of a solvent, that's the guy that does the dissolving, and the solute, and that's the guy that is being dissolved. Okay, and we are focusing on what's called an aqueous solution. We're going to focus more on those liquid solutions. Remember this, and how if we have something like salt, water is going to come in, and the negative part of the oxygen is going to have a force of attraction between that positive Na, and of course then the positive from the hydrogen part of the water is going to be attracted to the negative, let's say chloride, and so again we have them surrounded in this way. So there are 2 factors, the natural tendency of those substances to mix on their own, and then of course the IMFs. So pause, what do those things mean to you? So the natural tendency is really the mixing, right? Is the mixing going to occur on its own? And when we think about gases, chapter 10, you should remember that mixing of gases is spontaneous. They do it on their own. They're going to naturally mix. Now, the formation of solutions, however, is going to increase in entropy, and we're going to talk a little bit more in detail about entropy in chapter 19 when we go back to thermodynamics. But for this point, you just want to know that entropy just means disorder, and that should make sense. If we're putting 2 things together, we're making a mixture, a solution, that means we're going to increase in the disorder. It's no longer going to be a nice crystalline NaCl particle. It's no longer going to be H2O molecule. Now we have a mixture of lots of different things, so we're increasing in disorder. So when solvent or solute is a solid or liquid, intermolecular forces are really important in determining if that solution will form or not. So pause the video, read the question, see if you get the right answer. I hope you did. And if that's not understanding, please ask in class. So the effect of intermolecular forces, how are these affected? Now, there's going to be three things to think about when we're talking about intermolecular interactions in that solution. First is the solute, right? How is the force of attraction in that solute going to come apart? How are those NaCl bonds going to break and come apart to be part of the solution? And then we have the solvent. Now let's think about the water, right? We just learned in chapter 11 that water has hydrogen bonding. Well, those hydrogen bonds or those hydrogen forces between those molecules need to spread apart enough in order for the Na positive and the Cl negative to be surrounded by them. So those are the two parts that need to be separated out. So hopefully that gets you to think about endothermic, right? We're breaking bonds, endothermic. We're separating those IMF forces, that's endothermic. And then, of course, how they're going to come together. How is that H2O going to surround itself, going to come together, going to now have that attraction around the positive Na, or have that attraction around the positive Cl, so, the negative Cl. So how is that going to come together? So that should think about exothermic. So your first two steps in the formation process are going to be endothermic because we're pulling things apart. And your last step there, that number 3, is going to be exothermic because you're bringing them together. So this is just terminology, fill in the blanks. Hopefully it makes sense. So this is what's really happening, and again, you've seen this before over and over again. You're going to see it on a free response question that we're going to practice if we haven't done it already at this point. But again, you have NaCl in water. What happens here on the molecular level, you have that Cl minus ion being surrounded by the H plus. You have that Na positive ion surrounded by the O negative, right? And there's your ions that are hydrated in solution because now those ions are surrounded by those water molecules. So the water separating out is going to be endothermic. The NaCl busting apart into those ions, right? They're busting apart, that's endothermic. But here, when they're coming together, when that attraction is pulling themselves together and those ions are being hydrated, that's going to be exothermic. So we can read this over, see if you can come up with an answer. Read that over again. It's a strong explanation, but really what's happening is like dissolves like. That's really what they're explaining, but in a more detailed version. So, of course, everything is energy, and everything is based off of enthalpy, right? Is it an exothermic heat energy change, or is it an endothermic heat energy change? So we want to remember that we dissolve solutes in solvents to make solutions every day, just like salt and water to make pasta. We take CO2 and we add some syrup to it to make our soda, and that's where we get all those bubbles from when we open up a can. Gasoline is a mixture. That's why you have your various types. You have your regular, your plus, and your supreme, because it's the amount of your solute that's in your solvent. So again, making a solution takes 3 steps, so we should be able to go through this kind of quickly now that I've explained it. So the first part, of course, is breaking that solute bonds. Number 2 is separating the solvent away from each other, those liquid IMFs. And then 3 is the mixing, them coming together in some way. So it all takes energy. Steps 1 and 2 would be endothermic, again, because we're breaking apart or separating. And step 3 would be exothermic, because we're bringing them back together. So just like Hess's law, we add them up. We add up the steps. However much energy 1, 2, and 3 steps take, will take how much the delta H of the entire solution is. So just like a regular energy diagram, we have reactants. We're going to break those apart. We have our solvent that's going to separate out. We have our solute and solvent making the solution coming together, which could be exothermic if the amount here, right, is more than our delta H1 and 2, or it could be endothermic, right, if our delta H3 is less than the combination of delta H1 and 2. So this helps us determine, though, if a solution will form or not anyways. And again, Hess's law, we just add everything up. So salt water is an example. Diluting HCl is an example, and oil and water are all examples of how like dissolves like. And we want to remember there are so many more ways for solutes and solvents to actually mix than for them to stay apart. In other words, if I put salt into water, it's going to spontaneously become that solution, versus if I take oil and water, the solution is not going to occur. So again, these are other nice visuals to look at to make sure you're understanding why is this exo and why is this endo. So again, the pictures are very, very similar, but it's the overall delta H of the solution that we really want to concentrate on. Again, give it some thought, so read, hopefully you get the answer. And that should make sense now. So I also want to remind you that we're talking about the solution that we're going to use maybe in reactions, but it's not a product, okay? We're not thinking about the nickel chloride here, in other words. This is an aqueous solution. I get that, but this solution came from the reaction that we formed, okay? Like your double replacement reactions that we did back in chapter 4, right? Your net ionics. That's not really the solutions that we're talking about. We're really interested in the solutions that we would use, let's say, in that reaction, the HCl aqueous solution, not necessarily the product. So just keeping that in mind, because some students in the past have gotten confused on that. You know, are we talking about a reaction that's occurring? And yes, it's a reaction, but it's not really, I shouldn't say it that way. It's a process, right? The solution making is a process. If it was an actual reaction, you know, we might get some explosions and things like that. So we're really not talking about that kind of reaction. We're talking about a solution process, how the solute and solvent come together and make a solution. See you in class.